Okay, good morning. Is the board?
Yeah,
Yes.
it's visible. Yeah.
Okay, okay. The board is clearly visible from all the edge. What I have written, and this board is clearly visible for you, all guys. Yes.
Yeah, it's visible, but in the lower end, yeah, it's fine. It's manageable. Yeah.
Okay, okay, okay. So, is there any non-correlations here in this class?
Yeah. There are few.
Okay, 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 fine. So here today we can start with atomic structure. So in atomic structure is actually somewhat in inorganic aspects is there and also some quantum mechanical aspects is also there. Here we are mainly dealing with the quantum mechanical, that is physical aspects of atomic structure. So you know what is an atom. So what are the particles having in an atom? So all the minute details, that is the basic details that you have to know, that you should know, and I think you might know all those things. So mainly I'm starting with the fundamental particle that we know, that is proton, neutron, electron is the major fundamental particles in an atom, right? So some of the properties, these are essential for the major calculations that we are dealing with, the problems associated with atomic structure. So some might, these values should not given in the question papers. So we have to know these values. This is a basics value. Okay. So I think you all should have to keep in mind, remember these values for the proton, neutron, electron, mass and charge of these particles. Okay, fine. You can write it down now, or we will share these screens, or we will share the records further as per whatever it is fine. Okay. So when this quantum chemistry or quantum mechanics, why it arises? Actually, before we are dealing with this quantum mechanical concept, there is another method is called classical mechanics. In classical mechanics, all the particles are treated to be macro in size. So there are so many properties are associated with this classical mechanics. So after identifying all these fundamental particles, they are to be micro. The classical mechanical concepts, so many properties are associated with classical mechanics. They are all, they cannot be they couldn't correlate with these microparticles. So there are properties that properties cannot couldn't be correlated with this microparticle. So in order to analyze what are the properties, what are the major contributions to each of functioning, in order to analyze all those things, we have to introduce a new theory. So they had introduced this quantum mechanical theory. They are mainly dealing with microparticles. Okay, that is proton, neutron, electron. These are not only our microparticles. There are some kind of neutrinos are there, anti-neutrinos are there. Okay, so all kind of microparticles and the properties of microparticles are coming under this quantum mechanical concept. So before it starting as a quantum mechanical concept, there is some kind of technical term called black body radiation. I think you might have studied this black body radiation in the beginning of quantum mechanics in your degree classes. Okay, so what is a black body? A black body is a body which absorb all kind of radiation on its faults. Okay, then if we stimulate that body by any kind, if we can increase the temperature, if we can just put it in a vary the pressure, if any kind of stimulations or if any kind of disturbance that we are giving to the body, that body will emit all radiation which absorbs. That is a black body. So black body is a body which absorbs all kind of radiation on it, it falls. when we disturb by means of any stimulus, it emits that all radiation which absorbs. So there is a property. So I think I can wipe clear this board. Okay, so this black body, the stimulus disturbance can be varied by in terms of temperature, pressure, or anything. So I'm going to plot as energy distribution versus wavelength. Okay, so once so many that black body absorb a certain kind of radiations or some kind of wavelength or a light's wavelength is absorbed now, then I'm considering three different temperatures, T1, T2, and T3. They are in the order of T1 greater than, T2 greater than, and T3. If I'm applying first the lower temperature, T3, it emits in this manner. I will plot all the functions and after that I will explain. Okay, so this is the graph corresponding for T3. If we are increasing the temperature, the energy level of that emitting radiation will increase. This is T2. And again, I'm increasing the temperature. The graph will be like this. So if we increase the temperature to the black body, the radiation, the energy of radiation is goes on increasing corresponding to the lambda max. So this is a single wavelength. Okay, so corresponding to the single wavelength, the energy distribution is goes on increasing as we increase the temperature. That is the disturbance to the black body. Okay, this is the observation that they were found at that time. Okay, so after finding out these concepts and these observations, there are so many theories came to support this quantum mechanical aspects. So there are some minor theories are there. So we don't want to go for that so much the earliest theories. We are just focusing on the important theories. So we are going to start with Bohr's model of atom. Okay. Before that, Dalton's atom model is there. Rutherford atom's model is there. We are not considering that as much. We are focusing only on the major theories. Okay. So first we have to go for the Bohr's theory, Bohr's model of atom. So according to Bohr model, there are some postulates for Bohr's model. That is, he considered the electrons are revolving through a definite path. In an atom, electrons are revolving in a definite path. They are called orbits. Okay, I will share the notes. Don't worry. Electrons are revolving through a certain fixed path. They are called orbits. And the main second postulate is this electron can exchange or change energy these electrons can change energy when it jumps to either higher or lower energy state. This electron can change their energy only when it jumps to either higher or lower energy state. Why this states as such an important in the sense? Previous model, that is came before the Bose model, what they had actually meant that by revolving in a fixed path itself, they are losing energy. That was the concept that found in the earlier times. Okay, while it revolving in a fixed, let us consider, we know now what is shells. Orbit are now we are calling as shells, right? K shells at the L, M, N, all are shells, that is orbits. Okay, suppose an electron is revolving in L shell, it is considered it is revolving in L shell. While revolving in a fixed orbit or fixed path, while revolving itself they are losing energies. That is what the concept it were found, they have think it taught in earlier days. Okay, so we know that electrons, these are charged particles, right? So if a charged particle is continuously moving, what happened? As goes on, as this moving is going on, it will degrade or it will collapse. That was the concept, but that was not happening at all, isn't it? And if an atom is not at all rupturing after we are keeping it for a law, isn't it? So if that concept exists, the no atom will exist at all. That means neither atom has stability at all. That was the if that earlier concept exists even now. Okay, now that is why this Bose second postulate has such great importance. That energy change, if an electron have to change their energy, that is happening only if jumps to either lower or upper energy level. Otherwise, it always constant while moving in a fixed energy level. Okay, so this has that much of great importance than the other theorem. After the Bose model, there are so many models are there. Sommerfeld model is there. Even though there are some limitations are here for the Bose model, and that they are also that limitations are overcome by this Sommerfeld model. But even though that Sommerfeld model is not taking as much as the Bose model, because he explained a lot to an atom, to the particles. So, which gives a clear picture about what is an atom and what is an electron, how it would be, how it would behave in an atom. Okay. So the third postulate is the angular momentum of an atom or an electron is an integral multiple of h by 2 pi. It's a constant. Okay, angular momentum is an integral multiple of h by 2 pi. It's a constant value. So we can write it as angular momentum is L, which is equal to integral multiple of, integral means n. We can take the values for n from 1, 2, 3, 4, etc. by 2 pi. Okay, so these are the main three postulates for the Bose model of atom. So let us go for some kind of formula derivations. So the smallest atom, that can easily solvable is our hydrogen atom, because in hydrogen there is only one electron is there, and isn't it, only one electron and one proton is there, there is no neutron. Okay, so the interactions, okay, what are the interactions, what do you mean by interactions? If more than one particle is there, we have to consider the interactions between each particle. Okay, here we have only one electron and one proton, so only one kind of interaction is there in between electron and proton. So hydrogen is the simplest atom that can solve easily. Okay, what do you mean by the solving? Actually, you might people might have studied Schrodinger equation, all those things, right? In quantum mechanical, Schrodinger equation is there. So you have heard about wave equation. What is wave equation? Psi. And what is psi square? What is the difference between psi and psi square? And all those things we have heard about, isn't it? So they have their own importance in quantum mechanics. Okay, psi is a wave function. As far as we have, my name is Jitin. So I am identified by my name, isn't it? Around my friends or in in my lab, I'm identified by from my name. So for each electron, they are identified by means of their wave functions. Okay, isn't it? Okay. Then what is psi square? Psi square is the probability density. Okay. There is a huge difference between psi and psi square. I think there is a graph that explains what is the difference between psi and psi square in your textbook. If you are plotting a psi like this, if you are plotting psi square, it will be like this. Okay. For a same wave function, psi would be like this, psi square would be like this. So psi is a wave function, psi square is the probability density. Probability density means we have to find out the density function, where the electron density is there in the orbital. Okay, that we can find out only by squaring the wave function. If you find out the integral by means of only by psi, it will cancel each other, because one positive thrust is there and negative thrust is there, so it will cancel each other. So in the same manner, we are taking here the hydrogen atom for the comparison for all other atoms. Okay, so hydrogen atom, I'm just simply writing the formulas. There is no need for the detailed derivations. Okay. So the radius of orbital, nth orbital. Okay, radius of nth orbital. So which is given by n square h square divided by 4 pi square m e square z. N square h square divided by 4 pi square m e square z. Apart from n and z, n is the number of orbital. If I want to calculate the radius of third orbital, we have to put n as 3. For here, hydrogen is atomic number. Z is the atomic number. For hydrogen, it is 1. Okay, so apart from this n and z, all others are constant. H is a Planck's constant. 4 pi m is the mass of electron, and E is the charge of electron. Okay, in order to solve all those things, we will get n square by z into 0.529. This is in terms of angstrom. Actually, now we are representing the radius in angstrom unit. That is into 10 to the power of minus 10 meter. So this is the radius of nth orbit. So actually this derivation came from this hydrogen atom. So we can apply this formula only to the hydrogen-like atom. What do you mean by this hydrogen-like atom? There is only one electron in hydrogen. So there is only one kind of interaction is there. Similarly, you have to make, if you are going for any other atom, you have to make it as hydrogen-like. Okay, for example, it is lithium. Okay, it is lithium. How will you make us lithium as hydrogen like? By removing two electron, it will become lithium 2 plus. Now this lithium 2 plus as hydrogen like. Not exactly, it is like. There are so many approximation methods are there. This is not the exact value. There are so many approximations because if you are making this as 2 plus also, just electrons are getting removed. Okay, that protons are still in the nucleus. That is why it is getting positive charge. So there are so many additional interactions would be there, but we are not considering that additional interactions as the major consequences. Okay, we are neglecting those interactions and considering that into as an hydrogen-like atom simply. So there are so many variations should be there, but here we are not considering that as much. Okay, so next is, this is about the radius and we have to calculate the energy also. The energy of nth orbital is, it is negative in sign because stabilizing energy. Negative 2 pi square z square m e raised to 4 divided by n square h square. So here also n and z are the variables and all others are constants. So I'm keeping that variables here, z square by n square. And here energy can be expressed in various units. Okay, so as for varying the units, this constant's value should also get varied. Okay, if I want this energy term in terms of joules, sorry, in terms of electron volt, that is the unit that normally we are expressing, we have to use this 13.6. Now this is in electron volt. Okay, if you want this in centimeter inverse, you can use this Rydberg formula. That is Rydberg constant that people are normally used in order to find out the energy transition between Lyman series, Balmer series, Baskin series, Humphrey Fund, that kind of series, that is line spectra of hydrogen atom. isn't it? So the you people can use this.
Sir,
Yes,
how is 13.6, sir?
13.6. Yeah. Then if you want to use in joules, I'm writing here. I think if people can see this, that is 2.178 into 10 to the power of minus 18 z square by n square. This is in joules. Okay. Here n represents the number of orbit, which orbits energy you have to find it out, that you can put it here. Okay. So from this, I'm going to derive another equation that you people might know. So I'm starting with energy in centimeter inverse. Okay. So that is minus RH z square by n square in centimeter inverse. So I'm considering any two energy levels. Let it would be E1 and E2. Okay, I'm just considering E1 and E2. So the energy of first level is E1 is equal to minus RH into Z square by 1 square, and energy of second orbital is minus RH into Z square by 2 square. Okay, so I'm just taking the difference, that is delta E. Delta E final minus initial, isn't it? So minus RH into Z square by 2 square minus of RH into Z square by 1 square. So this delta is nothing but E2 minus E1. So it will become plus. The common terms are RH and Z. We are considering for a single atom, right? So I can replace this because this is minus and this is plus. I'm taking RH and Z square as outside. This become 1 by 1 square by 1 by minus 1 by 2 square. So actually this is RH into Z square 1 by, this is n1 square minus this is n2 square. This is the familiar formula for you guys. Actually there is a Z square here. We are normally using this, we are not putting Z here generally because we are using this for hydrogen atom. Lyman series, Balmer series, brackets, Pascal series, bracket, Fund, Humphrey, this series are only for hydrogen atom. We are normally supposed to use for the calculations also for hydrogen atom. That is why we are not putting Z here, because for hydrogen it is 1. If you are going other for other atoms, we have to put it here. Okay, so this RH value is what I have written just before in different units. Okay, again I will write. So this RH have different values in centimeter. This is in centimeter inverse. This is an electron volt. This is in joules. So those three different values can also put it for there also. Is it fine? Are you guys fine with this? Is there any?
Sir.
Okay. Shall we go for a problem now? A simple problem in order to identify these terms, how to substitute, how to getting the values. Hello? Hello?
Yes, sir.
Yes, sir.
Okay. So please write it down. The relation between ground state energy of hydrogen, and first excited state energy of helium plus. Relation between ground state energy of hydrogen and first excited state energy of helium. You can take ground state as n equal to 1. Here we are considering electronic energy levels, not as vibrational rotational kind. So we can put here n as 1. Can you please work it out now? It's not a single valued answer, it is a relation. Is there any relation is there? This we have to analyze. That is all. Just simply substitute the in final equation. Okay, you can retain this constant as it is. For helium, you have to change the atomic number, and keep in mind that it is first excited state, not first state. So all the terms, you have to read properly the question and keep in mind all the terms while selecting the formula and also for the substitution. It's done. Hello? Hello? You complete this?
Yes, sir.
Yes. What was the answer for hydrogen atom? The energy of first orbital? It's Jitin, right?
So minus 13.6 electron volt.
Minus 13.6 into 1 square by 1 square. That is minus 13.6 electron volt. For helium plus atom in first excited state. So which is the first excited state? This constant is the same. Here it is numerator, it is Z value. What is the atomic number of helium? Hello?
2,
Two.
sir.
2. So it is 2 square. So which is the first excited state?
Second level.
Second one. So those are exactly the same. So is there any relation? Both are the same. That is the relation. Got it? Fine? Okay. So next is photoelectric effect. Photoelectric effect. You know very well what is actually photoelectric effect is, isn't it? So when a suitable, what do you mean by when a radiation is falling on to a metal surface, some of the electrons get ejected from the metal surface. So this ejection of electron is happened only when a suitable wavelength falls on it. Okay, so the energy corresponding to eject the electron should be comparable with the energy of coming light. Okay, so this is the metal surface. Consider this as the metal surface. Radiation is falling on to the metal surface of the metal surface. So electron getting ejected. I'm considering this metal surface. Suppose this is an iron atom. Okay, iron metal. Okay, I'm simply considering iron as an atom here. So this ejection of electron is happening from which orbits? Is it from the inner orbit or from the outer orbit? What is the probability? The ejection is from inner orbit or from outer orbit?
Outer orbit.
Outer orbit, obviously from the outer orbit. So I'm just drawing only the outer orbit. So here the radiation is coming. So electron has to be ejected from here. So the energy of this radiation, what is actually called it as? If we want to eject the electron from the outermost shell of an atom, so the energy corresponding to that is what you may call. That is a technical term, right? the energy required to remove the electron from the atom. The outermost shell of an atom in a gaseous state is called as
Ionization energy.
the ionization energy. So, what we are considering, what we are actually meaning to be is, if we are supposed to give the energy equal to the ionization energy, then only the electron get excited, sorry, ejected. Okay, that is why we are using cesium metals. In generally in photoelectric effect, we are mainly mentioning that for metal like cesium. Why it is cesium? Cesium has the lowest ionization energy. Okay, generally this energy in photoelectric effect we are defined as the work function. Okay, the minimum energy required to eject the electron, and this minimum energy is actually the ionization energy of the corresponding atom or the metal that we are using. Okay, so we don't know how much energy that we are using for. Okay, so simply I'm giving an energy of radiation of h mu. Actually, this h mu is the sum of the minimum energy and the electron is going out. That is half mv square. That is kinetic energy of electron. So this kinetic energy simply I'm writing as Ke, which is equal to h mu minus h mu 0, which is equal to h of mu minus mu 0. And this h mu minus otherwise can be written as psi, that is work function. And this equation is known as photoelectric equation. This gives the relationship between frequency of radiation and velocity of electron. Here v is the velocity, here mu is the frequency. Okay. So while we are supposed to allow the light falls on the metal surface, the electron is getting ejected. There, there are two kind of phenomena are here. That is how fast these electrons are moving. That is one thing. Okay, how fast these electrons are moving and how many numbers of electrons are producing within a particular time. Okay, these are the two important factors we have to mainly focusing on about photoelectric effect. Okay, so what are the parameters which controls these two? Okay, the numbers of electron producing from the metal surface in a particular time, and also the energy of electrons, that is energy in the sense how fast they are moving. Okay, so only we can adjust the frequency as well as the intensity of the light. By adjusting those two only, we can adjust these two values, two factors. Okay, by adjusting these two, what they have found out is for controlling the kinetic energy, we have to vary the frequency of light. That is, kinetic energy is linearly depending on the frequency of light that we are used, not the intensity of light. Kinetic energy is proportional to the frequency, and the intensity is proportional to the numbers of ejected electrons. So from this, the questions may ask like that by drawing the plots. From the plots, you have to identify these things. Okay, if I am giving a plot like this, so which is the correct graph? Which is the correct graph among these three? One, two, and this three.
Second one.
Second one. Okay, if kinetic energy intensity is coming, the graph should be like this. There is no change as varying the intensity, and here also the number of electrons is not depending on frequency, so the graph should be like this. Okay, if n and I comes like this, the graph would be n and I, it would be like this. They are linearly varying. That also you have to keep in mind. So this is also a kind of increment, right? This is also a kind of increment, but this is not linearly increasing. This is exponentially increasing. Our graph is something about linearly increasing. So problems related to photoelectric equation can also be asked in order to finding out the velocity or work function, the minimum frequency like that, or minimum wavelength or any kind they can ask. Okay. Next is Heisenberg uncertainty principle. Heisenberg uncertainty principle. according to Heisenberg uncertainty principle, the definition you might know, it is impossible to determine the position and the momentum of a particle simultaneously. That is, two properties of a microparticle cannot be measurable. It is not measurable simultaneously. That is what he said. So there is always some inequality is in between happening. So once we can measure one property, and by keeping constant of that property, we can measure the other one. If you are considering that as to be constant, actually it is not a constant one. These are all up to the assumptions only. Okay, generally we are Heisenberg uncertainty principle, we are talking about this position and momentum. Now this is not only for position and momentum. For any two properties that are related to the microparticle, that is for electron that we are considering now, they are obeying the uncertainty principle. Okay, position and momentum, if you are considering for position and momentum, delta x into delta p, which is greater than or equal to that constant h by 4 pi, and we can also this used for energy and time, h by 4 pi, or simply we can write it as h cut by 2. Here h cut is h by 2 pi. This energy you can write it as h delta mu, and this momentum is also you can write it as m delta v. Okay. You people that have you heard about this commutative properties, that are the four major properties should be allotted for a wave function? The major properties for wave function and all those things you people know? Hello? How to define a commutative properties? How can we define this? Operators, operations, and all those things you know? Hello?
So we have a rough idea only.
A rough idea only. Yeah. Okay. Anyway, today we will just briefly explain all those things, and then at the second class we have to complete this atomic structure in the second class. So in that class, we just go somewhat deeply into the quantum mechanical aspect. That is about commutators, what is commutator, what is operations. I think you people have about these 6 postulates of quantum mechanics. You know what are they? The 6 postulates, or 6 or 5. The last one is not considering as much. You know what are the postulates of the quantum mechanical concept?
Yes, sir.
Yes, then fine. So according to that, we have to derive not the derivation. So in among this, there is a postulate that for every measurable, observable property, there is a corresponding operation in quantum mechanics. There is a postulate like that. For every measurable and observable properties, an operation should be here in quantum mechanics. That is a postulate for the quantum mechanics. I think it is second or third one. So as per, we have to know the operation, the operators of each properties. That is, we know what is Hamiltonian. I think you people might know. Hamiltonian is the somewhat linear operator. There are some technical terms that we can go for the next class. So here now we can just briefly explain what about the basic concept. Okay. So next is dual nature behavior. Dual nature behavior. So why this dual behavior comes? Because this electron, the microparticles, can act as both as particle and also as wave. So I just explained this photoelectric effect, right? So photoelectric effect is giving more support to particle nature of light. Okay, and some interference, diffraction, and also some physical phenomena. Okay, physical phenomena more going for, it's supporting for that wave nature. Okay, so this particle, this light wave, light has both particle as well as wave nature. So you know how they can combine together. That is done by de Broglie. So according to de Broglie, lambda is equal to h by p, where p is mv. For particle have velocity, only particle have the momentum, and wave has the wavelength. So this is the relationship between particle nature and wave nature. Fine. Additionally, just note it down, a technical term called Compton effect. Compton effect. Compton effect. So what is actually Compton effect is, if you are allowing a light falls onto a metal surface. Okay, so if it falls onto a metal surface, some energy can gained or lost by the light. So the metal surface can add up energy to the light. It is a possibility, or it can absorb energy from the light. So these are the two possibilities, isn't it? So these two possibilities are included in Compton effect. So as per Compton effect, what he said is decrease or increase in wavelength or energy. Decrease or increase the energy or wavelength of X-ray. We are mainly here focusing on X-rays. After scattering from a surface. After scattering from a surface. Is defined by Compton. And this effect is called Compton effect. So after scattering, the light may, after the scattered light may have energy lesser than the incident one or higher in wavelength than the incident one after the scattering phenomena. So that phenomena is known as Compton effect. Why this decrease in energy or increasing in wavelength is happening? That is what he explained in by Compton. This is already explained by also in somewhat in similar manner of Raman effect. You know Raman effect. What is Raman effect? There is a Rayleigh scattering is there. Raman scattering is there. So the electron in the metal surface is getting absorbed by the energy from X-ray. So that is why the scattered X-ray has lesser energy than the incident one. That is the explanation given by the Compton.
Sir, can you repeat it once again?
Okay. So the Compton effect is actually the scattered X-ray light has the lesser in energy than the incident one after scattering phenomena. So this scattering, this decreasing energy, why it is happening so? The electrons in the surface, electrons in the metal surface or whatever the object that we are using, these electrons are getting absorbed by the energy from the X-rays. So the after scattering, it is deviating. Scattering is a phenomena, it can deviating their path. Right. So if you want to, if you are coming in this way and they are deviating their path. So in order to split it off, it takes some kind of energy. And also the electron also getting absorbed energy from the X-rays. So after all this phenomena, these lights are coming out from the object. So obviously the energy is getting decreases when we comparing to the incident X-ray light. Is it fine?
Yes, sir. Thank you, sir.
Okay. So this phenomenon is observed by Compton and phenomenon called Compton effect. Okay. Is there any questions or doubts regarding up to this class
Sir,
taken? Hello, Shamir.
sir, in spectroscopy, we studied about Stokes line and anti-Stokes line in Raman effect.
Yeah, Raman effect.
Is there any relation between the Compton effect and that Stokes line?
That is Raman effect is actually completely what they it is also scattering phenomena. Compton effect is actually an in the stimulus to in order to finding out the Raman effect. Actually, Raman got somewhat inspired by means of Raman effect actually observing by only a few less than and 1% of particle is undergoing for Raman scattering, right? And all others are coming for Rayleigh scattering, isn't it?
Okay, okay, sir.
So
Yes.
this is the why this that small fraction is also having this phenomena. That is what explained by Raman effect. So there is no nothing common in this Compton and Raman effect. Okay.
Okay, sir.
Is it fine for all of you? Hello.
Yes, sir.
Okay, so next is actually something about this starting, that is introduction to the quantum mechanics. So what is a quantum mechanic concept? What is a wave function? How we can solve this wave function by means of Schrodinger equation? So what is the simplest form of Schrodinger equation? What are the operations? What are the representations and some then quantum numbers, then I told what is commutator. So that is something important because that we can use for in order to analyze. I have already told that this Heisenberg uncertainty principle, right? So why this is uncertainty in? So what are the properties are uncertain in order to find it out simultaneously? So that we have to find it out. Now we can simply list it out that position and momentum is uncertain and energy and time is also uncertain in some aspects. So is there any other variables that are uncertain that we have to know, right? So these are all can be find it out by their commutative property. Okay, we know that what is actually commutative property? A plus B equal to B plus A. That is actually commutative. But when it comes to operators in quantum mechanics, it is not always to be the same. A plus B not to be equal to B plus A in some cases. So if you are taking the difference, A plus B minus B plus A, if it is not equal, there is some difference. There should be some difference, right? For not all the cases, or in some cases, it not to be equal. So it should be having some difference. So if there is any difference, it is not commutative. So they can measure simultaneously. If it is commute, that is A plus B equal to B plus A, so the difference is 0. Right. So they are not they are commute, so we cannot identify. So there is a theorem, like not theorem, we can identify from that also by doing the commutative property. So in order to working out this commutative theorem, we have to know the operations corresponding to all variables. For position, there is a corresponding operation. Momentum, there is a corresponding operation in quantum mechanics. For all the each parameters that we are saying simply, that is position, momentum, velocity, mass, and all those things, there is an operations in quantum mechanics. So that we have to list it out first. Okay. After that, we can go for commutation, association property, all those things. Okay. Is it fine?
Yes, sir.
Okay. So today we can wind up the sessions. I will send the notes up to here, and also some questions. I have some questions, and Dr. Sabil will send to you by Google Sheet or in WhatsApp that I will hand over to him. Okay, is there any questions from this portion that I have taken now? You can ask now. Is there any queries or any doubts or any concept or misleading or anything is here? Ask me.
Or if you have doubt in letter, you can send to me and I'll forward to him. So you can contact in that way too. So thanks, Jibin sir. Yeah, somebody asked something or yeah, okay. If there is no question, then we can wind up the session. As Jibin sir said, the lecture notes, I mean the notes and the worksheet, we will upload in the Google Drive. So you can get it from the. Well, anything else to know, Jibin sir, or is this okay? Hello, Jibin. Yeah, I know. Okay, then we can wind up the session. So I'm closing the meeting here.